good. Good morning, everyone. So today we have the pleasure to have Clifford Will. Cliff is a visitor. He spends all his summer since about 30 years in Paris. He was first a visitor at Observatoire de Meudon and then IAP. So Clifford Will is a distinguished professor at the University of Florida, and he's a member of the American Academy of Science. He's very well known for many important contributions in the field of general relativity, gravitation, relativistic celestial mechanics, foundations of general relativity theory. Let me just mention a few of his contributions. He developed in the 70s with Ken Nordtvedt a general formalism for testing gravity theory in the solar system called the PPN formalism, parametrized post-Newtonian formalism, which permit to test alternative theories of gravity in the solar system and in binary pulsars. He has many contributions on the theoretical foundations of general relativity. Notably, he contributed to our modern view of the role and of the equivalence principle in GR, in general relativity theory, or in the class of metric theories of gravity, I would better say. Cliff has received many distinctions and prizes. Let me mention that he received in 2021 the prestigious Einstein Prize of the American Physical Society. Cliff wrote several important books. Probably his best known book is Theory and Experiment in Gravitational Physics, which is a bedside book for any relativists in our field. With Eric Poisson, I would recommend his book on Newtonian, post-Newtonian, and relativistic gravity, which is full and replete of many interesting results on Newtonian gravity, even, and post-Newtonian gravity. And he is very well known in the grand public, for his book, Was Einstein Right? He will tell us the answer in his talk today to that question. So I would just say that Cliff is a pure classical general relativist. He believes that general relativity will be valid all the way until the Planck scale. Also, gravity has been checked experimentally only up to the millimeter scale. He has long been a killer of several alternative theories of gravity using his post-Newtonian PPN formalism. And he does not believe in any modification of general relativity to account for mysterious properties of dark matter. So today he will tell us about the rebirth of general relativity in the 60s. So Cliff, we look forward to enjoying your talk.
Mute.
Okay, this works. 1, 2, 3. 1, 2, 3. Okay, this seems to work. Okay, I apologize. Maybe you can instead.
Okay.
Okay, so after this, the theory was triumphant. Einstein became a major superstar, and everybody lived happily ever after. Now, the real story is somewhat more complicated than this. There was considerable skepticism at the time about Eddington's results, especially among American astronomers. At this time in history, physics in Europe and the United States was dominated by experimentalists, and they had no interest in nor patience with this complicated theorizing that Einstein had developed. And by the way, all this new theory seemed to do was predict minuscule deviations from Newtonian gravity, which were completely unimportant. And so as a result, within about 10 years, the theory began to a steep decline, so that by the middle 1950s, it was considered to be in the backwaters of physics and astronomy, not a suitable subject for a serious scientist to pursue. But beginning in the 1960s, all this changed, and a tremendous renaissance for general relativity began, fueled in large part by discoveries by astronomers of things like quasars, pulsars, and the cosmic background radiation. And by the end of the decade, in 68, 69, when I arrived at Caltech as a first-year graduate student, this relativistic wave was building up, and I happened to be at the right place at the right time to catch that wave. And by 1979, when Joe Taylor announced that he had measured the shrinkage of the orbit of the binary pulsar in agreement with the prediction of general relativity as a result of gravitational wave energy loss, this renaissance of general relativity was pretty much complete, and people from particle physicists to astrophysicists to astronomers were anxious to get in on the fun. So what I would like to do in this talk is give a bit of a history of this down and up story of general relativity. It's from the triumph of Eddington to the backwaters of science, the beginnings of this renaissance, a bit of my own story when I arrived at Caltech in 1968, 69. And then I want to finish by focusing a little bit on the binary pulsar and the aftermath of that and the beginnings of gravitational wave detection with laser interferometers to illustrate the synergy between theory and experiment. Something that was rather new for general relativity. We take this for granted in other fields of physics, indeed all of science, this necessary synergy between these two branches. This was lacking for many years in general relativity, but I think by 1979 and the ensuing decade, it became a key part of our subject, which is partly what's made it such an exciting subject today. Now, full disclosure, I am not a historian of science. So this history is going to be biased, selective, based on some of my own personal experiences. So, just bear with that. I'm a pure relativist, as Luke pointed out. Okay, so let's start with the beginning of the fairy tale, the 1919 eclipse expedition. This is really the product of thought and work by Astronomer Royal of Britain, Sir Frank Dyson, Arthur Eddington, a noted astronomer, both an observationalist and an accomplished theorist, and Charles Davidson, also an astronomer. You must remember this in 1915, when Einstein presented his theory, the world was in the First World War, and Germany was essentially cut off from the rest of the world in terms of scientific exchange. However, Willem de Sitter in neutral Holland was able to get copies of Einstein's paper and forwarded copies of that to his friend Eddington in Great Britain. Eddington then realized that this new theory was a remarkable development and produced a long report on it for the London Physical Society. And with Dyson, they prepared and got funding for an expedition to the May 1919 eclipse in order to measure the deflection of light that was a key prediction of this theory. Eddington, who was a member of the Quaker religion and a pacifist, also believed deep in his heart that the idea of having British scientists verify the theory of a German scientist would help to bring about reconciliation among the nations and produce world peace. He had been a great scientist, but he wasn't much of a realist in terms of politics, but it was a deeply felt. Indeed, he had been exempted from serving in the army because he was a Quaker. But in the late stages of the war department was so desperate to get more soldiers to send to the front for the final push, they threatened to revoke his exemption. But an appeal by Frank Dyson convinced them to keep him exempted from serving in the army, and so the preparations to go forward for the expedition. On November 11th, the war ended, and in April, two teams departed for Sobral and the island of Principe. So here's the world showing the path of totality. They left England for the island of Madeira. The two teams split up. One went to the city in northern Brazil. Davidson and Cromlin went to Sobral and set their telescopes up at the Jockey Club there. Eddington and Cottingham went to the island of Principe, which is a part of the two-island colony, San Tomeo and Principe, which is at that time was a Portuguese colony. And they made their measurements during this total eclipse. Now on Sobral, they had two telescopes, a 4-inch and a 13-inch, but as is often the case, there was cloudy weather during the eclipse, so the number of stars they could see wasn't optimal. And apparently the 13-inch telescope spontaneously changed its focal length during the eclipse, maybe due to thermal effects, and so they never used that data. The 4-inch telescope gave 7 plates, each showing 7 spots surrounding the sun. And of course, to measure the deflection, you need to take a photograph of the same field of stars to show, so that you can measure the tiny deviations of the images when the sun is present compared to when the sun is absent in that part of the sky. So they made those comparison plates on July 11 and departed back for England on July 22nd. En principe, Eddington and Cottingham had just one telescope. There was a big rainstorm in the morning, and Eddington feared that he would not get in whatsoever. But finally, this clouds cleared just enough to allow them to get 2 usable plates with 5 stars each. For various reasons, because they were much further east, they didn't make comparison plates there, but made them earlier in the winter using the Oxford telescope. They left Principe on. I'm sorry? Okay, it's when I wave my arms, it's hard, right? They left for England on June 12th and arrived in Liverpool on July 14th. There was the results. Now, the popular history seems to say that it was all Eddington. Eddington was the only one who was doing this, but in fact, the Americans were eager to do this as well. In fact, William Campbell and the director of the Lick Observatory in California and his colleague Heber Curtis were anxious to actually beat the Brits to a test of GR. So they took existing photographic plates of eclipses, one in 1900 near Augusta, Georgia, and the other eclipse in 1918 in Goldendale, Washington, on the west coast of the US, and analyzed those plates to see if they could see the Einstein deflection. Unfortunately, the images were poor, and they could find no ambiguous evidence for Einstein's prediction. In fact, Campbell traveled to London for the summer 1919 meeting of the Royal Astronomical Society and reported at that conference that he was unable to measure the Einstein deflection. In fact, at that same conference, Dyson read a telegram that he had just received from Eddington, who had just boarded a ship to return, Eddington saying that he expected to have a positive result when he finalized the data analysis. And so the results that were reported from Sobral on the 4-inch telescope, they measured a deflection of 1.98. This is the deflection projected to the limb of the sun, which in general relativity is 1.75 arc seconds. So they measured 1.98, but in agreement with the GR prediction to about 7%. And en principe, they had a result also in rough agreement with GR to about 17% precision. Certainly, these results disagreed with the Newtonian prediction, which is 1/2 of that effect. Now, during the 1980s, historians of science began to write papers criticizing Eddington, arguing that, first of all, he really believed that general relativity was right. He was so impressed with it, he thought it must be right. And they asked, why did they not use the 13-inch data? Was it because it disagreed with general relativity? So basically, they accused Eddington of either massaging, ignoring, or using maybe unconscious bias in the way he treated the data. Interestingly, around the same time as these papers were being written, a group in Oxford reanalyzed the Sobral plates. This was the 100th anniversary of Einstein's birth. So in honor of that, they reanalyzed both the Sobral plates, both the 4-inch and 13-inch. Eddington's plates at Cambridge seem to have been lost or destroyed in the interval. So the 4-inch plates gave a result pretty much the same as what they had analyzed in 1919. The 13-inch plates also gave a result in rough agreement with GR, but with larger errors, as you might expect, because of the added uncertainty due to the focal length issue. So our colleague Daniel Kennefick, who is both a general relativist and a historian of science, wrote a book recently analyzing the entire result, and his conclusion was, on balance, there's no evidence for Eddington having cheated or being biased in any way. They analyzed the data the best they could, did the best job they could with what they had. Well, Eddington was a master of publicity, and so he set up his announcement at the November 1919 meeting of the Royal Society of London and the Royal Astronomical Society with the press present, big expectations. And so the scene was captured by Alfred North Whitehead, the great mathematician, saying the whole atmosphere was exactly that of a Greek drama. And in the background, the picture of Newton to remind us that the greatest of scientific generalizations was now, after more than 2 centuries, to receive its first modification. And of course, after the announcement, the press went wild. The next day, the London Times reported revolution in science, Newtonian ideas overthrown. 2 days later, in the New York Times, men of science more or less agog. Notice only men of science in those days. Men of science more or less agog, not completely agog, just more or less agog. Stars not where they seem, but don't worry, it's not a problem. Anyway, so you get the idea of this feverish result of this announcement, and this is what made Einstein an overnight celebrity. And of course, he became a celebrity basically for the rest of his life, his picture destined for coffee mugs and t-shirts everywhere. So here he is in a ticker tape parade in New York, celebrating his achievement. In Hollywood, chatting with the film star Charlie Chaplin. Here he's interacting with the press. And here he's in Arizona visiting the Hopi Indians. So his fame was secured because of this event. And this is sort of the fairy tale part of it. Now, while people in the US were initially skeptical of the results, Campbell and Trumpler, during an eclipse in 1922, did get a result that was in agreement with general relativity. So that kind of dampened the American skepticism somewhat. On the other hand, there was a bit of a backlash against Einstein, especially in Germany. This is now the 1920s with the rise of Nazi ideology. And some of this was promoted by Philippe Lenard, who won the Nobel Prize in 1905 for his work on X-rays. The idea was that they denounced this kind of fancy theoretical Jewish science as exemplified by Einstein in favor of more Aryan-based science, which was tied closely to experiment, as again, experimentalists dominated the scene in those days. Another important test of general relativity was the gravitational redshift. In fact, Einstein regarded this effect, the change in frequency of light as it goes up or down in a gravitational field, as the most important of the tests that he had. He had 3 key tests: perihelion of Mercury, deflection of light, but it was the redshift that he thought was the key test of the theory, because it was really a foundation of the whole thing. In fact, he first had this idea in 1907, later calling it his happiest thought. This is the idea that light in an accelerating laboratory in free space should be the same as light in a laboratory at rest on the surface of the Earth, an equivalence between acceleration and gravity. And if you think about the accelerating elevator, you'll see that a photon emitted from the top will appear to be blue shifted when it reaches the bottom, simply because the bottom is moving higher at a faster velocity. So he had the gravitational redshift already in 1907. And when the full theory came along, it just came out of the mathematics in a straightforward way. So the obvious thing to do was to try to measure this effect. And that was attempted by people like Charles St. John, great spectroscopist of the day. A team at the Kodaikanal Observatory in India tried it, and they were unable to detect the redshift of spectral lines from the sun. And some historians of science think that this hurt Einstein's chances for the 1918 Nobel Prize. And as we all know, he didn't win it until 1922, and that was for the photoelectric effect, which did have a strong link with experiment. But in 1925, Eddington entered the picture again. Here, the idea was to measure the shift of spectral lines not from the sun, but from white dwarfs. You'd expect a much bigger shift, maybe 10 to 100 times bigger, because white dwarfs are of the same mass as the sun roughly, but 10 to 100 times more compact, so the redshift is bigger and thus easier to measure. And so the idea was to measure the shift in the spectrum from Sirius B, which is a white dwarf companion to the dog star Sirius A, the brightest star in the sky. So Adams, a spectroscopist from the Hale Observatory in California, was going to measure the shift of the spectra of Sirius B, while Eddington would make a model of the white dwarf to predict its radius. Its mass was known just from the orbital motion around Sirius A, but you need the radius in order to predict the amount of redshift from the surface. And so Eddington, who was a great stellar model builder, would do the calculate a prediction for the radius and therefore the redshift. And in 1925, once again, in that referee journal known as the New York Times, the headline said, "New test supports Einstein's theory." Again, headlines about this wonderful new experiment. But within a year, it all began to fall apart. Astronomers criticized Adams' interpretation of the spectra, especially in view of the possibility of strong scattered light from the much brighter companion, Sirius A. And furthermore, by 1926, already it was known by people like Ralph Fowler at Cambridge and others that white dwarfs were not some extreme low mass object on the main sequence, but were governed by an entirely new thing, this newfangled thing called quantum mechanics. That the degeneracy pressure, the uncertainty principle acting on the electrons in these very, very dense stars would support them against gravity. And so their mass radius relationship could be much different from what Eddington used. This was long before Chandra-Sekhar's maximum mass. Already in the mid-20s, they understood that white dwarfs was something different because of quantum mechanics. And so they criticized Eddington's theory. So just as a postscript to skip ahead, in 1971, when the orbital motion brought the two stars right in the sky to reduce the scattered light effect, Jesse Greenstein at Caltech measured the spectra. They had better spectrographs then, so they get accurate measurements. And of course, by then they had completely valid and robust models of white dwarfs, so they could make the predictions. And the predictions agreed with the observations. The interesting thing is that the shifts were 4 times what Adams had measured, and the predicted radii were 4 times what Eddington had calculated. So Eddington and Adams agreed with each other, but they were both wrong by the same factor of 4. Again, historians of science had a field day with this, but again, on balance, they have decided that the two men did the best they could with what they had available at that time. So there's no evidence of collusion, but it's just remarkable that they were agreed, but were wrong. So it's a lesson about theory agreeing with experiment. You could still be wrong. And by 1950, Einstein had to admit, this was 5 years before his death, that the redshift effect had not been measured. There was simply no evidence for this test at that point that was, to him, the most important test of his theory. So by the 1950s, this was, general relativity was really in the backwaters of physics and astronomy. Our colleague, John Eisenstadt from the observatory has called this, who is a historian of science, by the way, called this the low watermark for general relativity. Very little was going on in the field. So, but I just want to give 2 anecdotes to illustrate this idea. First, in 1962, a young man was graduating from Caltech, getting his bachelor's degree, and was on his way to Princeton to do graduate work. This young man was told by a very famous Caltech astronomer, whatever you do when you get to Princeton, do not study general relativity because it will never, ever have anything to do with real physics. Luckily for me and many others, that young man, whose name is Kip Thorne, ignored the advice, fell under the spell of Johnny Wheeler at Princeton, and the rest, as they say, is history. Here's another example. That same year in 1962, there was an international conference on general relativity. It was still a small field, but they had started organizing triennial conferences. This one was in Jablana, Poland, near Warsaw. And in attendance at that conference was Richard Feynman, the great American physicist, to see what was going on in general relativity. And during the conference, he wrote back to his wife, because there are no experiments, this field is not an active one. So few of the best men are working on it again. The result is that there are a host of dopes here, and it is not good for my blood pressure. So this illustrates the whole viewpoint among mainstream physicists about the entire field at that time. But as I said, it's, the common saying in those days was that general relativity is a theorist's paradise and an experimentalist's hell. But then it all began to change. In 1961, the discovery of quasars, and a few years later, the discovery of their large redshifts, discovery of the background radiation, discovery of pulsars, and even the first black hole candidate in 1971 in the X-ray source Cygnus X1. And this really changed the scene. It implied that possibly general relativity might have something to do, after all, with mainstream science. And so in 1963, So in 1963, some relativists at the University of Texas in Dallas, Ivor Robinson, Engelbert Schucking, and Alfred Schild, decided to organize a conference to try to bring together relativists and astronomers and astrophysicists to try to attack this problem of the quasars. The conference, they already had in mind this would be a conference to establish a new field, which they called relativistic astrophysics, and was organized to be held in Dallas in mid-December 1963. Now, if you remember your American history, this was about 3 weeks, a little more than 3 weeks after the assassination of President Kennedy in that same city. So you could imagine the atmosphere in the US and in Dallas at that time, a very sad atmosphere, but very tense atmosphere. And here they were coming together to maybe begin a whole new field of physics. In fact, the conference was opened by Texas Governor John Connally, who greeted the attendees for the conference, but his arm was still in a sling because you may remember that one of the bullets that killed Kennedy actually went on and passed through his Connally's arm. So it was a very supercharged atmosphere for this conference. In attendance at the conference were 240 astronomers and astrophysicists and 60 relativists. And I've read the list of attendees, and that list, 60, consists of all the known relativists in the world at that time. The only ones who weren't there were the relativists from the Soviet Union and behind the Iron Curtain, the Soviet bloc countries, because of course they would not have been allowed to travel to outside those countries. And right after the assassination of Kennedy, America wouldn't have let them in anyway. So they were absent, but still 60 relativists. And various groups presented their ideas to explain the quasars. Willie Fowler and Fred Hoyle from Caltech and Cambridge talked about supermassive stars undergoing gravitational collapse, and so that potential energy would be released to produce this enormous power that the quasars seem to be producing. Tommy Gold and his collaborators from Cornell talked about supermassive star clusters, not gas, but the stars themselves also undergoing gravitational collapse to produce the quasars. John Wheeler brought his group, including a young student, Kip Thorne, to the conference. He was talking about analyzing the gravitational collapse of compact objects. They had in mind neutron stars, so they're not totally relevant to quasars, but they were doing things in a fully general relativistic way. So trying to understand, in broad terms, relativistic collapse. But strangely, it was all about the collapse. Nobody talked about the black hole itself as the central engine. That's the current view of what quasars are. It's things that go around the black hole. Whatever produced it has long since happened. It's the black hole that's the engine. But at that time, it was all about the collapse. Also at this conference, there was a very mathematical paper presented by a young man from New Zealand who was visiting the University of Texas at Austin called Gravitational Collapse and Rotation. This is a very mathematical thing with killing vectors, and the astronomers in the audience were scratching their heads. They didn't know what this guy was talking about. It was all very strange and new. And those who were at the conference vividly remember at the end of Kerr's talk, Achilles Papapetro, a Greek relativist, stood up and turned to the audience and said, I think we should pay close attention to what this young man has done, because I think it could be very important in the future. And of course, this was the Kerr metric that describes all rotating black holes in the universe. But some people at this conference were not so convinced that this would work out, this kind of feeling the love between astrophysicists and relativists. Phil Morrison, the MIT astrophysicist, said he was interested in all this getting together, but unpersuaded that it would work out. Peter Bergman, the relativist, said he wasn't very optimistic that it would all work out. But it turned out that Tommy Gold from Cornell had the last laugh on this idea about the relativists. In his banquet speech at the conference, he said, it was, I believe, chiefly Fred Hoyle's genius which produced the extremely attractive idea that the relativists, with their sophisticated work, were not only magnificent cultural ornaments, but might actually be useful to science. Everyone is pleased. The relativists who feel they are being appreciated, who are suddenly experts in a field they hardly knew existed, the astrophysicists for having enlarged their domain, their empire, by the annexation of another subject, general relativity. It's all very pleasing, so let us hope it's right. What a shame it would be if we had to dismiss all the relativists again. So this Texas Symposium in some ways was the beginning of this sort of official recognition of relativistic astrophysics and the buildup of this wave, this growth in general relativity in order to explain some of these astrophysical phenomena. So I appeared on the scene quite by chance. I was entered Caltech for graduate school in 1969, and I was in the right place at the right time to catch this growing relativistic wave. So here's a picture of Bridge Laboratory at Caltech where the relativity group was housed. This is an old picture of Caltech in what was then sleepy Pasadena. And at that time, Kip's group consisted of, well, there was a picture of Kip long before he went Hollywood. This group, all his students were working on the problems in this field of relativistic astrophysics. Richard Price was looking at perturbations of black holes. Jim Ipser was looking at these relativistic star clusters, trying to understand them, trying to explain if their redshifts could be gravitational redshifts rather than the redshifts due to the expanding universe. Bernie Schutz was working on problems in stellar structure. This is before his days as a gravitational wave physicist. Many of you know Bernie, and so on. So they're all working in various topics in this new field of relativistic astrophysics. Now, although I was born and raised in Canada, after 1 year at Caltech, I had fully converted to the Southern California lifestyle. And I had written a term paper in Kip's course that he seemed to think was pretty good. So he invited me to start sitting in on his group meetings. And so I sat in, I didn't know what was going on, had no clue, as many young students do the first time they go to a group meeting, say, what? But a momentous event occurred that spring, June of 1969, when Joseph Weber announced in the New York Times and in Phys Rev letters that he had detected gravitational waves. Weber, of course, was using large solid cylinders of aluminum. We call them Weber bars today, solid cylinders. He glued at the midpoint, around the midpoint of these cylinders, piezoelectric crystals, so that when a gravitational wave came by, it would stretch and squeeze the bars lengthwise, producing strains in these crystals that then produced an electric current. The electric current fed into a strip chart recorder. It's like the pens on a lie detector. So you have a strip of paper that can be miles long, and as the paper moves, the pens go like this, recording the noise in the detector and maybe recording a signal. And you would examine these strips to see if you can get a gravitational wave. But Weber, of course, established a principle right on that is now used in LIGO, in fact, in all the detectors, that you needed two detectors widely separated so that if you saw some sort of event, to guard against it being some random noise, if you saw the same event in two well-separated detectors, you had a candidate for gravitational wave. And this is what he claimed. He had a detector at the University of Maryland, where he was a professor, and one at Argonne National Laboratory near Chicago. The problem was he was reporting strengths of signals and frequencies of signals that were unbelievable. They could not be explained by what anyone thought at that time. He was seeing events several per week, several per day. And you could not, you might be able to explain them if you had a supernova, near us in the galaxy, but 3 per day, I mean, it seemed impossible to believe. But another alternative, as Kip expressed, was that all these estimates of the flux of gravitational waves from astrophysical sources use general relativity. So maybe general relativity is wrong. And so he pointed at me, hiding behind Richard Price, I think, and said, Cliff, find out everything you can find out about how right general relativity is, because maybe it's wrong and Weber has proved it. So we need to find out. And so that summer, I spent time trying to learn all I could about the tests of general relativity. So in 1969, this is how right Einstein was. 1964, Dickey at Princeton had verified to a factor 100 better than the famous experiment by Utfush at the turn of the 20th century, that bodies fall with the same acceleration, irrespective of their composition. The gravitational redshift was measured for the first time, not by astronomical means, but in a laboratory measurement that measured the shift in the wavelength or frequency of gamma rays emitted by radioactive iron from the top of a tower on the Harvard campus to the bottom, and they also did it vice versa. So they measured it, the redshift in the laboratory. The first measurement of the solar shift was done by Brault, a student of Dickey's, to about 5%. The perihelion advance of Mercury, another cornerstone of Einstein's theory, was known only to 20%. And this is, again, by learning about Mercury's orbit, by studying transits of Mercury across the sun, and doing all by optical means. The reflection of light from solar eclipses wasn't known any better than it was in Eddington's day. It was good to about 10% from an eclipse measurement done in 1952. And to make matters worse, Dickey himself, with his student Carl Brands, had invented a theory, we now call it scalar tensor theory or Brands-Dickey theory, that could satisfy all the experimental tests if you chose a value of the coupling constant, omega, to be about 7. So it was a completely viable theory of gravity. On the other hand, in my reading, I learned that some help was on the way. Things were developing that could change this situation. For example, the technique of radar ranging, bouncing powerful radar signals sent from Earth off a planet and measuring the round trip travel time, promised to improve the accuracy of planetary ephemerides. Much more with a dramatic improvement over optical measurements that were the mainstay at that time. Erwin Shapiro at MIT, then at MIT, one of the pioneers of radar ranging, also discovered theoretically what he called the fourth test of general relativity. This is what we call now the Shapiro time delay, the excess delay in the propagation of light as it passes by a massive body, for example, on its way to a planet or on its way to a spacecraft. A few years later, Shapiro also proposed to measure the deflection of light using radio interferometry and get away from these optical measurements that require a solar eclipse. You can look at the sun in radio wavelengths any time of the day. And NASA was considering at that time, this is the middle of the Apollo project, putting a laser retroreflector on the moon. This is a special kind of mirror that takes a laser beam and reflects it back exactly in the same direction from which it came so that you could measure to high precision the Earth-Moon distance. I went up to Jet Propulsion Laboratory. Kip said, go up there and talk to the people there who are running the Mariner 6 and 7 projects. After making his prediction of this time delay, Shapiro and his team had measured it in 1968 by bouncing radar signals off Venus and Mercury. But at JPL, they were running the Mariner 6 and 7 encounters with Mars. After those encounters, those spacecraft were scheduled to go off to the far side of the sun, and they could also measure the time delay. So I was sent up there to find out, what kind of accuracy did they expect to achieve compared with the radar ranging, bouncing signals off planets. But that summer was when I made what I call the big discovery. I discovered 3 remarkable papers by a young scientist named Ken Nordtvedt Jr., who was an assistant professor at Montana State University in Bozeman, Montana. What he had done was taken the post-Newtonian metric of general relativity, which is a formula with some set of terms, and instead of the numerical coefficients that appear in GR, he stuck an arbitrary parameter in front of each term and then calculated things to see how they would depend on these parameters. And what he discovered was that if you take he used point masses in his picture of matter, but if you took a collection of these point masses, what relativists call dust, that were bound together by their own mutual gravity, and asked what would be the acceleration of that gravitationally bound blob of dust in an external gravitational field. He discovered that it would, in general, depend on its internal gravitational binding energy. It would not fall with the same acceleration as any other body. The more compact it was, the different it would fall compared to a less compact object. This effect actually did not occur in general relativity. These parameters, if you put in the GR values, the answer would be 0. There's no effect in GR, but in the scalar tensor theory of Brands and Dickey, there would be an effect. And so he had this idea that it would affect the Earth-Moon orbit because the Earth and Moon would fall with a different acceleration toward the sun, and that would induce a perturbation on the orbit. And he proposed testing that in the third paper using lunar laser ranging. Well, this is quite a remarkable discovery that alternative theories could have such an effect that things like the Earth and Moon could violate the equivalence principle. Now, it turns out that in my term paper for Kip, I had studied Chandrasekhar's post-Newtonian formalism, which was based on hydrodynamics, perfect fluids with pressure and energy density and so on. And I realized that I could generalize Nordtvet's formula to hydrodynamics, so you'd have a much more realistic version of the bodies that you were studying. And working with Kip as my advisor, we decided to call this a PPN, or parameterized post-Newtonian formalism, that would be a way both to study alternative theories and to see what experimental tests would tell us about the theories. But in some ways, the true origin of what has is today called this framework came in Bozeman, Montana, a year later or so in 1971, when Nordtvet organized a summer workshop on the topic. And thanks to the incessant nagging of one of Kip's students named Shandor Kovac, he basically told Nordtvet and me that we needed to combine our formalisms into one. We used different notations, we had different parameters. He used points, I used fluids, blah, blah. If we didn't combine them and collaborate on this, this formalism might not have the impact that it could. So in the end, we did, mainly to shut him up, but we did it. And these are the parameters that now that people use. Gamma, for example, controls the bending of light. Gamma and beta control Mercury's perihelion advance. But there are parameters that are zero in general relativity, but they tell whether or not the theory predicts that a moving system will behave differently than a system that's at rest with respect to some preferred frame, such as the cosmic background reference frame. So there's no such effects in general relativity, but there can be effects, and there are well-known theories that do have such preferred frame effects. And over the years, all these parameters have been bounded, all in agreement with general relativity, to precisions ranging from parts in 10 to the 5 to parts in 10 to the 20, depending on the parameter and what you're looking at. So this has become a tool then for testing theories, comparing theories, and even suggesting new experiments. And in some ways, this decade, after I graduated, was what we soon after called the golden age of testing general relativity, because many tests were, it was a decade full of experiments. The Shapiro delay, for example, was measured using Mariner 6 and 7, Mariner 9, culminating in the Viking landers on Mars, measuring this effect as gamma parameter to 0.1%. We now know it to about a part in 10 to the 5. The gravitational redshift effect was measured now using atomic clocks, which had been steadily developing over the years. In the famous experiment Gravity Probe A, putting a hydrogen maser on a rocket in a suborbital flight, comparing that hydrogen maser with an identical one on the ground. And here's Bob Vassaux and his colleague Marty Levine holding up one of their hydrogen maser clocks. Mercury's perihelion, now using radar ranging to improve the knowledge of its orbit and the orbits of all the planets, was then, with an accumulation of 10 years of data, known to 0.5% compared to the 20% earlier. And soon after Neil Armstrong put the first retroreflectors on the moon during Apollo 11, people started being able to send laser beams to that reflector and measure the distance to the moon in those days, sub-meter levels. They're now working at millimeter levels. And then again, an accumulation of data showed no evidence for the Nordtvet effect down to a level of about 0.01 in 1976. And of course, no Nordtvet effect agrees with general relativity. So the next great event in this saga, this renaissance of general relativity, occurred in 1974. In 1974, I had arrived at Stanford as a brand new assistant professor. I was there to, in part, work with Bob Wagner, one of the great astrophysicists of the day. He was famous for his calculation with Fred Hoyle and Willie Fowler, the first robust calculation of Big Bang nucleosynthesis, calculating all the abundances of the elements, light elements, that come out of that process just after the Big Bang. But after Weber's claims of detecting gravitational waves, he had turned a lot of his attention toward general relativity and gravitational waves. And I was sitting in my office. I just settled in. This was about middle of the month, middle of September in 1974. And Bob burst into my office waving a telegram. Now, when I tell this story to young people, their first question is, what's a telegram? This wasn't just any telegram. This was an IAU telegram. And for those who, everyone in this building should know what it is. The International Astronomical Union in those days, and they're just housed in this building, used to send a telegram to all the universities, observatories, and institutes around the world to announce any new discovery in astronomy so that other astronomers could follow up on the detection. And so Bob came in waving this IAU telegram saying, Cliff, they've just discovered a binary pulsar. Whatever you're working on, you've got to drop it. We've got to work on this thing. Wagner is one of the most enthusiastic scientists I know. He's just overflowing with enthusiasm. So whatever he's interested in at that moment is something we just all got to do. So he quickly wrote a paper pointing out that there would be this gravitational wave damping of the orbit, and predicted that at the current levels of accuracy that Taylor had, they would be able to detect this effect within about 15 years. And I wrote a paper on the implications of the pericenter advance, which had not yet detected, but if they did, how that would impact alternative theories of gravity. And many, many other people jumped on this and wrote lots and lots of papers about this new discovery. By the way, this telegram, if anybody can help, this telegram is from the same era. I would love to get my hands on a copy of the actual telegram that announced the binary pulsar, if it exists somewhere in the IAU archives. I couldn't find it online. And of course, this was the binary pulsar discovered by Russell Hulse, Taylor's PhD student, who was at the Arecibo Radio Telescope, our dearly departed radio telescope, studying pulsars. And he found this pulsar whose period was kind of strange. For a time on September 12th, for example, it was more or less constant. But then over a 120-minute period relative to zenith, it decreased much more rapidly and by much more than normal pulsars do. The next day it decreased even more. And then the next day, September 16th, it decreased and then began to increase again. Very quickly, Hulse realized that this was not a crazy pulsar. It was a normal pulsar, but it was in a binary system. These changes in its period were just due to the Doppler effect of its orbital motion. And then with Taylor, they got together and determined the parameters of the system and began to study it in great detail. And this culminated, of course, in their famous announcement in December 1978. It was then the 9th Texas Symposium on Relativistic Astrophysics, this time in Munich. And what I've shown here is a function of time from 1974 to about 2010. This is the time of pericenter passage, which if the orbital period is decreasing at a roughly constant rate, then this time should decrease quadratically with time. And this curve, of course, is the accumulation of all the 30 years of data. The error bars, the little error bars you see in the size of the dots, have been expanded by a factor of 400 relative to the actual error bars. And the curve is not a fit to these points. This is the prediction of general relativity. Once you know the two masses of the two objects, you know everything else about the orbit. So it fits absolutely beautifully. Now this box, of course, shows the data that Taylor used to make his initial announcement in 1978 that they had measured the rate of change of the orbital period, and it agreed with general relativity. And of course, as we all know, in 1993, they shared the Nobel Prize for this wonderful discovery and their analysis. But strangely enough, about 2 weeks after the announcement that they had won the prize, I received a fat envelope from Sweden, from the Nobel Foundation, with all kinds of gold lettering on it and stuff, inviting me to attend the Nobel Prize ceremonies as a guest of the Nobel Foundation, not as a guest of Taylor. I mean, I knew him, but this was from the foundation itself. The letter also said there'll be all expenses, stay at the Grand Hotel, we'll fly you to Stockholm business class. Then the letter went on to say, well, if you bring your wife, she can come too, and everything's expense paid. But if she comes, you have to fly economy class. So I had to think, business class versus economy class with my wife. What should I do? The fact that I'm here alive tells you that I made the right decision. And I'll just show this picture. You may be shocked, but just to prove that every once in a while I know how to dress properly. Okay. So let me turn to my final sort of topic. It still has to do with the binary pulsar and what followed from it, but I want to emphasize this idea of the synergy between experiment and gravity. So again, 1974, the discovery of the binary pulsar. By the way, 1974 was also the first numerical head-on collision of two equal mass black holes by Larry Smarr and his collaborators, just as a point of history. But in 1976, a paper appeared in Phys Rev Letters written by Jürgen Ehlers, Josh Goldberg, Peter Havash, and Arnold Rosenblum that made a lot of us very unhappy. Made us unhappy in the same way that when your mother tells you to eat your vegetables because they're good for you, it makes you unhappy. Not because you know she's right about eating your vegetables. They are good for you, but you don't want your mother telling you to eat your vegetables. So what Ehlers et al. Did was to state that the interpretation of the binary pulsar, and especially once they measure the damping, which hadn't been measured just yet, is based on what's called the quadrupole formula, a famous formula derived by Einstein, but also derived later by other means, that gives the flux of energy away from the system due to gravitational waves. And basically the bottom line of that paper said, there is no evidence that this quadrupole formula is an actual prediction of general relativity. They had a list of 7 things that were wrong with all the work that had been done to date. And these people were not crackpots. Ehlers was one of the great mathematical relativists of the 20th century. He founded the Albert Einstein Institute in Bonn, Germany. So he was a serious scientist, Josh Goldberg, and so on. They were all serious people. I won't give all 7 things that they said were wrong, but just I'll talk about a few. They argued that you use multiples to calculate the gravitational energy flux, just as you do in electromagnetic theory. You calculate dipole radiation, quadrupole radiation in electromagnetic theory by calculating the multiple moments of the charges, and their various time derivatives gives you the flux. The problem is in general relativity, it's not just mass that produces gravitational waves. Each mass has its own gravitational field that varies with time, and the field extends to infinity. So when you calculate your multiple moments, you have to integrate everything over infinity, not just the mass of the bodies, but also their fields. And if those fields don't fall off fast enough, you could get integrals that diverge. That if you take the integration variable to infinity, you get infinity. So, and I can attest to the fact that that happens, because around the same time, Bob Wagner and I were calculating the first post-Newtonian correction to the quadrupole formula. And I can assure you that we swept many, many divergences under the rug. Okay. Another criticism, people talk about the energy flux at infinity. And then they say that this loss of energy is equal to the loss of orbital energy, and that's what makes the orbit shrink. They called it energy balance. Ehlers et al. Argued there's no proof in general relativity that that is true. No one has ever shown this. It's an assumption. It seems reasonable, but there is no proof. And furthermore, the calculations of the actual radiation reaction forces within the binary that you could calculate are so poorly done that they're unbelievable. And in fact, there are contradictory published results that disagree with each other in the literature. So these are just 2 of many criticisms that they had. So like the kid with the vegetables, when you look at the paper, you thought, I gotta say they're right. Like we're sort of annoyed that they were telling us all these terrible things that we had to fix. And so the discovery of the binary pulsar and these set of criticisms forced a lot of us to begin to take seriously the foundations of all these calculations of equations of motion and gravitational waves and radiation reaction that we had kind of taken for granted and swept under the rug for many, many years. Now, of course, in 1979, they measured the damping of the orbit, and it was in agreement with the quadrupole formula. But as we saw in the example of Adams and Eddington, having agreement between theory and experiment is not so meaningful if the theory is in fact wrong or is unreliable. So it really became important because of this observation to shore up the theory, and a lot of us began to work on this during the 1980s. And then in the early 1990s, the stakes were raised in this whole enterprise because people starting to think about the designs for laser interferometric gravitational wave detectors realized that you would need to have predictions for the gravitational waveform from inspiraling, say, binary neutron star systems to very high accuracy in order to maximize the chance of detection of waves and the chance of measuring things like the masses of the bodies and getting science from those detections. So we were being told by people at LIGO and Virgo that we had to calculate these gravitational waves to very high PN order, not the quadruple formula, not the 1 PN order that Wagner and I had done, but to higher and higher order, 2 PN, 3 PN, and maybe beyond to get the maximum out. And so basically we had to do a lot of additional theoretical work and to do things, of course, in line with Ehlers' criticisms. And many methods were developed over the years. The multipolar post-Minkowskian framework that Luc Blanchet, Thibaut Damour and their collaborators developed. Our work at Washington University then called direct integration of the relaxed Einstein equations, the Jena group with Tomasi in Japan. In more recent years, effective field theory from particle physics. Many new techniques were developed to try to build up this knowledge of gravitational waveforms for LIGO and Virgo while still adhering to Ehlers' complaints. And it turned out in 1999, I gave a talk reporting progress in this whole field at a seminar in Kyoto, Japan, and Jürgen was also speaking and was in the audience. And so several people in the audience turned to Jürgen after my talk and said, well, Jürgen, are you happy now? And Jürgen, being Jürgen, said, we got him to admit that he was happier than he was, but he's still not totally happy. And if you know Jürgen Ehlers, you know that much is a complete stamp of approval on what we were doing. So he was happier. And by the way, again, motivated by the pressure to have gravitational waves in time for a potential detection by LIGO, the numerical relativists were not idle. And this famous breakthrough in 2005 in numerical relativity really allowed us to combine post-Newtonian calculations with numerical relativity and get waveforms that were useful for science. So I just want to close. So people now in the field, of course, think it's all a fairy tale today. General relativity is very exciting. We've got multi-messenger, we've got gravitational waves, imaging of black holes, all kinds of cool things going on in the field. And so we forget sometimes that things weren't always this vibrant in our field. But I just want to give one example just to illustrate the difference over this past between the 60s when I was young and just starting out and today. So you recall this 1962 meeting in Jablona, Warsaw, where Feynman made his famous complaint. At that meeting, there was one talk on experiments. But there was one talk on experiments. It was given by Vitaly Ginzburg, the great Russian scientist. Since the conference was in Poland, obviously he could go to that conference, and one talk on experimental gravity. In 1922, there was at GR22, sorry, there was in 2019, there was a GR meeting. It's the 22nd in the series in Valencia, Spain. At that meeting, 10 of the 18 plenary talks were on observation or experiment. There were 3 talks on all the major types of detection, ground-based, LISA, and pulsar timing arrays. There were talks on the Event Horizon Telescope's images of MME7, a talk on observing the stars orbiting Sagittarius star, the black hole at the center of our galaxy. There was a talk on precision observational cosmology. There was even a talk on analog gravity, efforts to find in laboratory systems, exotic laboratory systems like Bose-Einstein condensates and other things, evidence for Hawking radiation within the laboratory. And then another talk was given. It was the opening talk of the conference, given by me, as it turns out, because this was the 100th anniversary of the beginning of the fairy tale. This was 100th anniversary of Eddington's big measurement. So I gave a talk detailing that story and also talking about updating everybody on the current status of experimental tests. So perhaps young people think they're in a fairy tale today, but I hope I've given you some insight into the history of the field. It wasn't always so wonderful, had its ups and downs, but today we're fully full-fledged physicists and astronomers, just as important and active as anyone, any other field in physics. Thank you.
Thank you very much, Cliff, for this beautiful talk. We shall take question now from all of you. Is there a first question?
Hello, thank you very much for your talk. With Luc and his former student François Laroutourou, we proposed to measure the periastron advance in an exoplanetary system. What do you think about the interest of such measurements?
Another question?
Yeah, in the period of low waters you mentioned in the 40s and 50s, what was the situation with general relativity in the Soviet Union? You said they did not participate in the first Texas relativistic meeting. In the early 60s, Zeldovich has started working on that. But before Zeldovich, what was the situation? Landau and Lifshitz had already made their books, their series of textbooks. How did they consider the general relativity in the Soviet Union?
Oh, yeah. No, there are indeed some big centers for general relativity there. Zeldovich, centered around Zeldovich, many of them. And I can't speak much about the 60s at the time of the Texas Symposium, but certainly by the time I was a graduate student, for example, Kip was going to Russia almost every summer to work with Novikov, for instance. And so, in fact, Kip contributed chapters to Zeldovich and Novikov, the famous book on relativistic astrophysics. So, despite the Cold War politics, there were lots of contacts between the two realms. Yeah, I'm just not as familiar with the history. I mean, we know about Landau and others, and Landau and Lifshitz, but I'm not that familiar with that part of the history.
Okay, so next question.
Thank you. Clifford, together with the revival of general relativity as a research field, what influence did it have on the evolution of teaching this topic? Not only textbook writing, but that universities that previously ignored it started teaching it. Then a follow-up question, since you are grandfather, I recently became grandfather, what is the youngest age a human being can start comprehending those concepts? Consider your grandchildren.
No, there was in terms of teaching general relativity and textbooks on general relativity around this same time. Earlier textbooks, like textbooks by Singe and Muller, had been very, very formal, very mathematical, emphasizing, very formal aspects of the subject. The big change came with, in 1972, with two famous textbooks, Weinberg's textbook on general relativity and Misner, Thorne, and Wheeler. Completely different approaches to the subject. One more field theoretical, more a particle physics approach. The other based on geometry and so on. But for example, they all had chapters and sections on experimental tests. Weinberg had several chapters on observational cosmology. When I was a postdoc with Chandra, he told me once that Weinberg's chapters on observational cosmology are the best he'd ever read, including those written by any astronomers. So he said they were just brilliant, these chapters. Oh, you all know Weinberg was brilliant at writing textbooks on almost any topic. But Misner, Thorne, and Wheeler had many chapters on experimental tests. They had chapters on black holes. Some talk about accretion onto black holes. So these were much more physically oriented rather than mathematically oriented, despite all the geometry that's in Misner MTW. But they really, at the end of the day, were focused on the physics. And then many textbooks to come were also that way. So I think that really changed how the subject was taught. And I think made it much more attractive to certainly physicists who wanted to study the field, because they could actually learn physics that they could work on once they knew some general relativity. And what's the youngest age at which a person could comprehend? My grandchildren, well, no. I have no idea.
Cliff, you mentioned the force test, the force classical test of general relativity, which is a time delay, the Shapiro time delay. But it was discovered by Shapiro in 1964. But Einstein, as early as I think 1912 or 14 maybe, he had written the geodesic equations for a photon. And when you have the geodesic equation, you have not only the trajectory of the photon, but also you have the motion of the photon on this trajectory. So it is very surprising that Einstein never thought about the time delay. Right. So do you have any idea about that?
Yeah, I mean, so he calculated gravitational lensing, for example. He wrote down the gravitational lens formula in 1912. It was wrong by a factor of 2, yes, based on an older theory, but still everything was there. The magnification of the sources, it's a beautiful thing, but only discovered 20 years ago by Jürgen Rand and others pouring through all of his detailed notebooks and papers. But he didn't do the follow-up. And I think it's partly because of technology. You could calculate it, but there'd be no hope of ever measuring it. But Shapiro was around at a time when they were developing radar ranging, and he got intrigued by it, by the topic, by hearing a relativist talking about the speed of light should vary. And he told me that, surely that's wrong, because, in general, special relativity, the speed of light is constant, but of course it's an apparent slowing down of light due to the curvature of space and so on. So he started to scratch his head about this, and had in mind, because he had been part of developing radar ranging, whether or not there was an effect. So he had a context to think about a delay, because he was building, at Haystack Observatory, building the big radio telescopes to send these megawatt beams of radio waves to planets. So he had a context in which to think that this effect might be there, and then he did the calculation.
Is there any, must be a last question? Okay, if not, so we thank you, Cliff, again, very much.
Là, il est à moins 21. Bah non, mais c'est vrai, on peut se demander qu'est-ce que c'est.